We are in section 4.3 on page 14. The first derivative test, give that a star, says let C be a critical value of a continuous function f of x, then f prime of x changes from positive to negative at C, then f has a local maximum. So if it changes from positive, so it's a positive slope, to a negative slope, that value up here is a maximum. Likewise, if f prime of x changes from negative to positive, then f has a local minimum at C. And the local minimum is because you're going from a negative slope to a positive slope, and so that would be a point down here at the bottom, which would be a minimum. And then it says if f prime of x has no change in its sign from left to right at C, then f has no local maximum or minimum at C. A visual approach to the first derivative test is given below. Let C be one of the critical numbers. And there's the 4 different scenarios that we could have, just for your reference. Next, it says steps to use the first derivative test to analyze critical values in analytically given f of x. So first thing is to find all critical values C. Again, to find critical values, this is where the derivative is equal to 0 or where the derivative is undefined. Using a number line, break the domain into open intervals using the critical values. Step 3, determine the monotonicity, whether f is increasing or decreasing of each interval. Step 4, if there is a change in monotonicity from increasing on the interval to decreasing on the next interval, there is a local maximum at f of C. And if there is a change in monotonicity from decreasing to increasing, there is a local minimum, just like what we have up above. Note, if the question says to find the x value of a local min or max, the answer is only C. If it says to find the local min or local maximum, substitute the critical value in and find the y value, f of C. So there's an example down here at the bottom of the page that says find the local maximums and minimums of f of x. So in order to do this, we need to find our critical values first. And so we're going to need to take a derivative. This function that we have is a polynomial, and so it's a continuous function, and it's also, domain is all real numbers. So taking a derivative, we have 3x squared minus 27. Factoring out a 3, we have x squared minus 9. And then in order to find our critical values, I'm going to set this equal to 0. You can factor it more if you want, or you can just say your values of x are going to be plus or minus 3. Solving that. So again, these are your critical values. So the next thing says, using a number line, we're going to break up our domain into intervals. So we're going to make a number line over here, and we're using our critical values that we just found. Also, notice that your derivative is defined everywhere. So we have no values for your critical values that are where the derivative is undefined. So we have 2 critical values. They're -3 and +3. And so we need to test, and we're going to go ahead and see about f prime of, and we'll pick something smaller than -3, we'll say -4. Something in between -3 and 3, I'm going to pick 0, substitute that into the derivative, and f prime is something larger than 3, we'll say 4. So substituting these values in to your derivative, the exact value does not matter. So if you were to look at your derivative and realize that if you have -4 squared minus 9, that's going to be a positive value, times 3 would still be positive. The next one is 0. If you were to substitute in 0, you do get a negative answer. And if you were to substitute in 4 squared minus 9 times 3 is going to be positive. So this goes from we're going to kind of just look at what's happening here. This goes from being increasing to decreasing slope. So that means at -3, we have a local maximum. So we have a local maximum and it's at -3, comma, f of -3. We'll figure out that y value in just a little bit. And then the next value, we go from a decreasing slope to an increasing slope, which means that we have a local minimum at 3, comma, f of 3. And then substituting those values into your original typed function, we get -3, comma, 34 for our local max and 3, comma, -74 for our local min. So this is how you would use the first derivative test in order to figure out local maximums and local minimums.